Welcome to Scholars Academy. If you are an ICSE Class 9 student studying geometry, you are exactly where you need to be. Today, we are going to uncover the hidden centers inside every triangle. To understand why this matters, think about two very different physical challenges. First, imagine trying to find the exact balancing point of a solid triangular plate. Now compare that to a planning problem. Finding a single location to build a cell tower so it sits exactly the same distance from three surrounding towns. You might assume you just need to find the center for both. But a triangle does not have a single generic center. Depending on the geometry problem you are trying to solve, a triangle actually possesses four completely distinct points of concurrency. Mastering these four distinct centers is how we move from simply recognizing basic shapes to calculating exact coordinates for complex, real-world spatial problems. Let's look at this textbook page. We start with the perpendicular bisectors. When you draw a line that cuts each side in half at a strict 90-degree angle, those three lines will always intersect at a single point. We call this point O the circumcenter. The circumcenter has a very specific geometric property. It acts as the exact center of a circle that touches all three outside vertices perfectly. Connecting the center to the edge of the circle, the line segments OA, OB, and OC are all equal radii. Now, instead of dividing the sides, let's divide the angles inside the triangle. If we draw bisectors for angle A, angle B, and angle C, they meet at a completely different intersection. We label this point I the incenter. The incenter forms the core of an incircle. Looking closely at this figure, you can see it is the center of a circle that fits completely inside the triangle, perfectly brushing up against its three inner walls, with its radius represented by the line IP. If you need to calculate the external boundary that contains a triangle, you use the circumcenter. If you need to define the maximum internal space within those walls, you calculate the incenter. Next, let's measure height. When you draw a straight, perpendicular line dropping directly from a vertex down to the opposite base, you get an altitude. Think of measuring the absolute vertical drop of a mountain peak. It forms a 90-degree angle at the bottom. A triangle has three vertices, so it has three altitudes. The specific coordinate where these three vertical drops intersect is called the orthocenter, labeled here as H. But an altitude is very different from a median. Look at the median diagram. The line segment drops from the vertex to the exact midpoint of the opposite side. It ignores 90-degree angles, only caring about cutting the baseline exactly in half. When you draw all three medians, they intersect at point G, the centroid. The centroid has a crucial mathematical property. It divides every single median into a strict 2-to-1 ratio. You can see the equations printed right here. AG to GM equals 2-to-1. The orthocenter gives us the mapping for the extreme heights of the shape, but the centroid, by splitting those medians perfectly, gives us the center of mass and balance. Let's put that 2-to-1 centroid ratio to work. Take a look at this diagram. We have a clean triangle with a median line, AM, that measures a total of 15 centimeters. Point G marks the centroid along that line. Our goal is to determine the separate lengths of segment AG and segment GM. Grab a piece of paper and a pencil. Go ahead and pause the video right here. Try to calculate the length of segment AG using that 2-to-1 ratio, then press play when you're ready. Here is how we break this down algebraically. Since the ratio is 2-to-1, we represent segment AG as 2x and segment GM as 1x. Added together, they equal the total length of 15. That gives us 2x plus 1x equals 15, which means 3x equals 15. Divide by 3, and our base unit, x, equals 5. To get our final answers, we just multiply that base unit. Segment AG is 2 times 5, making it 10 centimeters. Segment GM is 1 times 5, making it 5 centimeters. Knowing the unique properties of the circumcenter, incenter, orthocenter, and centroid turns a confusing web of intersecting lines into a reliable, solvable set of equations. Keep practicing your geometric proofs, and we will see you next time at Scholars Academy.